All right, we should be live now. Welcome, everyone. My name is Mark Hughes. I'm here on behalf of Advanced Assembly and Royal Circuit Solutions. And we're here for a tech chat with Mike Jouppi, or Jouppi. I mean, you can pronounce it however you want. Mike's too polite to say anything. Mike's joined us a couple years back, not years, but months back, and we were talking about thermal design because he is something of an expert in the area. He literally wrote the standard IPC 2152. I mean, it's all his data, all his hard work and research. And that led to a hack chat over at hackaday.com, which then brings us back to today. So, Mike, maybe give us a little history about what we're talking about today and what we're gonna do.
Sounds good. Well, first off, a lot of people contributed to IPC 2152. I did put in a big chunk in the very beginning, but there was a large team of people that came together, not only for writing the standard, but also manufacturers that helped build boards for us that more than myself and my company did testing. It just turned out that the test results from the work that my company did turned out to be the data set of choice. So we had this hack chat that you helped to inspire. And on Hackchat, I don't know how many people are aware of how Hackchat works, but you're just typing and getting messages from people through your online screen, and it's all typing, no video, audio type interface. So there's a gentleman that's working on his PhD, I assume in electrical engineering, that had a problem where he had 4 MOSFETs on a board, and each dissipating 15 watts. So he had 60 watts of power on this board. And he had a question about how to design the thermal vias for those packages. And right off the bat, 60 watts of power on a board is a lot of power. And the extremes that you have to go through to manage that power are all dependent upon what the application of that electronics turns out to be and how it's mounted and what it's mounted to. And it was just too difficult to ask all of those questions, not to mention just the electronics package that he was dumping this 15 watts into each one of them. MOSFETs, in my past, they're designed to handle a lot of power, but, the manufacturers of the components, they guarantee that the package can handle it, but what you do with it after that, once you mount it to a board, it's all on you, and it's not a simple problem. And so I reached out to Dan Maloney. Am I pronouncing that right this time? And I asked him to put me in contact with this gentleman that was working on his PhD, and he's in Germany. And so Dan reached out to him to allow me to communicate with him so that I could give him a little bit more information that I was able to help him with on that hack chat. And so what I'd like to do, what brought us together again here is to go over some of the tools that I sent to him to help him work through his problem. And the primary part of that is just this little calculator I put together in Excel. I mean, this isn't a software product by any means. It's a tool that, I built tools for the work that I would do when I was a thermal analyst out in the industry, and I built tools for every little kind of problem that I saw as something that would be repetitive. So it would help me speed up my process of design as I run into these common problems. So the main thing that I want to show, today and go over is this calculator for sizing thermal vias and how I put that together. And now, are you able to put that out there for people to download it?
Sure, we can put that up at royalcircuits.com/blog. I'll type that up and put it on the screen. It's not going to be there yet, but I will send it off to my boss and we can put it up there.
Cool. Yeah, the other part that's so I put a revisions page into it. So when I would ever give something away, I always included a revisions page. And in there, if people make changes to it, all I ask is that you document the changes you make to it. If you find an error, let people know you found an error, what the correction was that you made. And I also added another worksheet in there for calculating the power dissipation in electronic traces. And the cool thing about that calculator that I included is that it's got information in there that, so there's the revision page. And if we have time, we'll go over this power calculator as well. But right here, what I wanted to do is just provide a little bit of basics behind what the basically the thermal via calculator was doing. And I did not add anything on the power calculator. That wasn't really the point of it, but I probably should have. So let's go over to that page with the design that Sven was working on.
Yeah, so 60 watts is a ton of power. And we get all that through just ohmic heating inside the components, or is part of that generated inside the traces too? Do you know?
It's just the component.
Wow.
Yeah, that's the part that, and so one of the things that I brought up with Sven was that he needs to consider the losses in the conductors as well. And you can see, we didn't go over his design, but I look at this little picture here, and it's just a small little screenshot of the design. And those white spaces that I put up there, those four little white blocks, are the outlines of the FETs, the MOSFETs.
Okay.
And those MOSFETs, I'm surprised at how small a package are made these days for handling this kind of power. It's just incredible to me that you can put this much power in this size package. And that package outline is 6 millimeters by 5 millimeters. And so for me, I have to convert that over to English units. And that's 0.2 inches by 0.24 inches. It's less than a quarter inch by quarter inch with 15 watts. So what I think about when I start seeing power, I also want to know what footprint that power is being dissipated over. And so what that brings to mind is power density. And that's one of the big things that I pushed and tried to collect a lot of data on when we were developing IPC 2152, is that you want to be not only cognizant of the power losses in your conductors, but also if you pay attention to the power density, there's a lot to learn. And I developed this little software tool for looking at all of the data that we had collected. And power density is one of the pieces that I calculate when I use this tool and I dump it into a spreadsheet. I look at power, I look at current, I look at temperature rise, I look at the board configuration, how many copper planes are in it, all of the aspects of, and I was working on adding mounting configurations as well, because all of those things contribute to the overall heat transfer in the particular design. And mounting configurations sometimes have as much of an impact in terms of lowering temperature rise as the copper planes in the design do. So looking at this board here, those 4 spots, they are so close together. Considering that those squares are 0.2 by 0.24 inches square, that means that they aren't any more than 0.24 inches apart, and on the large dimension, and closer, that maybe a 1/10 of an inch or less, from side to side. So you're not looking at 15 watts of power. You're looking at 60 watts of power in a very small area. That it's probably 3/4 of an inch by a 1/2 inch that this design is trying to dump 60 watts of power in.
So something the size of a quarter.
Yeah, 60 watts. And it just, that gets exciting for me. I love solving problems like this.
So Mike, let me ask you real quick. You've got a different threshold from most engineers because you deal with space, or you've worked with space systems. But at what point should my spidey senses start tingling? At what power density? Do I need to start stopping what I'm doing and really start considering my power budget? Not my
You
power,
know,
but my thermal.
there's one more webinar I'd like to do with you, and that's to look at this calculator that I put together for looking at trace heating.
Okay.
And with that, we can get a sense of those kind of numbers,
Okay.
because it's too hard to throw out one number, because everybody's design is different. The size of the boards are different. I was at a conference once, and a guy came up to me and talked to me about a top secret design he was working on.
Oh, no.
And I'm a little bit facetious about top secret there. But he was working for an industry company that was, so the way he described the problem is a 1-inch cube. And he was going to be dissipating about a watt of power in that 1-inch cube. And I said, well, where's the energy going to go? And he goes, well, I don't know. And I said, well, if it's all by itself and it's dissipating 1 watt of power, it could just go to an infinite temperature with no energy loss. So you can't have energy in, you got to have energy out, and you have to understand what that energy out is. And he couldn't describe it well enough for me to really help him. And I said, well, you just got to treat it as a control volume, and you got to look at how the energy can get out of that little system, and then you can from there start to determine what kind of a temperature rise you have in your electronics. Well, in hindsight now, after time has passed and you see these little plugins that you plug into your wall socket, and you put in your charger, plug in, charge your phone. I think that's what they were. And in that case, had you been able to talk about it more, you've got a really good heat transfer path out of that cube to the wall socket, which is tied to copper wires that conduct that energy back through. And so that's the big heat sink in that design.
That makes a lot of sense, Mike. Yeah, and it also makes a lot of sense that the engineers for a lot of these, famous companies, the Apples, the Teslas, the SpaceX, they never want you to know what they're doing or who they're working for. Their bosses have scared them so much that they can't ask the right questions.
Yeah, and they're afraid of IP concerns and losing their IP, because people pick up on it so fast and they run with it so fast. It's amazing the development that can occur in a short period of time.
True.
And then it's their jobs that are on the hook. So I don't slight them for it, but you can only help so much when you have limited information.
Yeah, absolutely.
So back to these, if you look at those white areas,
mm-hmm.
I don't know if you can see underneath them. There's looks like 6 vias underneath.
I can.
And yeah, so I think those were the thermal vias that he had put into the design. So he had 6 under each package, and then an additional 6 there, kind of in the middle off to the left. Yeah, those guys.
Okay.
Yeah. And so what I'd like to do is just look at how I put together a calculation for the thermal resistance in the thermal via.
Sure.
And then, work that problem a little bit further and show how I worked through this to help Sven just kind of think about a few other items in his design.
Okay, so we've got 30 vias in an area the size of a quarter, essentially, a little bigger.
Yeah.
Okay, so would you like me to pull up the next spreadsheet?
Yeah, let's go to the calculator.
All right. I know initially we wanted you driving today, but technology just didn't want that to happen.
That's all right.
All right. So this is the spreadsheet that we will make available to people after the webinar.
Cool. Now, I've just thrown in some theoretical numbers. And what people are looking at here is, on the left-hand side are the material properties. I'm just using copper. I've got the thermal conductivity of FR4, polyimide, and an epoxy fill. And I'm in the calculations, we can, I believe I'm just working with FR4. And then down below that, I make the note that there's no radiation or convective losses, with one exception. And we'll talk about that. So here the goal is to have 15 watts of power. The next line down under power is a junction to case. So the junction to case thermal resistance, there were actually 2 values for these MOSFETs, 0.5 degrees C per watt and 0.9 degrees C per watt. And I never, it said typical for the typical is 0.5, but it could be as high as 0.9. And in design, you have to go with the worst numbers. You can look at it and start weighing decisions by looking at what the typical values are, but you wouldn't want to start there. And then the next line down is the case to board thermal resistance. On his design, he has some thermal interface material that he was putting in to provide a good heat transfer path between the case of the package and the board. And then the next line down, through board. So what I've done there, I've combined a few different calculations. That's actually, and I'll talk about that when we get a little further along, but it's basically looking at the thermal vias and the board material. But I don't separate the volume of the vias from the board material. It really doesn't matter too much in this particular case, but it's probably good to assess those kind of differences, to take that volume away if you're looking at a very specific design. And then the next slide down, the board to sink. So there's going to be, what he was working on with this design is he wanted a convective heat sink, some kind of finned arrangement on the bottom of the board that he was going to dump this energy to. And on any kind of heat sink like that, you have a thermal resistance between the board and whatever you're using. Just like the component to the board, there's always a thermal resistance there. And so I don't know what that number was. 1 degree C per watt is a low number. It could very well be higher. And you just have to cross that bridge when you come to. I didn't know what kind of a heat sink he was using. I didn't have any information. I just threw an optimistic number in there to make things look good.
Okay.
Not a conservative approach, but I think it's achievable. And then the next line down is conduction through the sink. So when you've got a convective heat sink, some finned arrangement, the energy has to conduct up through it. And quite often they'll give you some kind of parameters that will take that into account, but I didn't know what that was. And I wanted to make sure that he was thinking about that when he was out selecting parts for his design. And so I just threw, again, a not necessarily conservative number, the 1 degree C per watt, but I put something in there just to have a point of something that would make him think about it. And then the sink to air, depending on how that convective environment is, and this is, I colored that red because I say no radiation or convective losses. Well, there would be convective losses off this heat sink, right?
Mm-hmm.
And if you had air blowing, then you'd also have convection off the board, most likely. And so the number there, the sink to air, would be from convection for this heat sink. And so there is, that aspect of it. So there is convection in this problem, but it's just off the heat sink. And but I wanted to clarify that.
Okay.
And so when you stack that whole series, so that's like a series of resistors for your electrical analogy. And those resistors are all in series, and that sums to 6.7 degrees C per watt. And so if you multiply the 15 watts by that total of 6.7, you come up with a junction temperature further down there of 124.8 degrees C. So I'm assuming a 25 degrees C ambient. If you click on the junction or the case temperature, and then click up on the equation up in the function line, you can see what lines, it's picking from.
That's much faster, Mike. Thank you. I was highlighting them individually.
No, there you go. And so that, that's how the case temperature is calculated, and also adding then the junction for the 124.8 down below. So now let's go over to where I'm actually calculating the thermal resistance through the thermal vias.
On the same slide?
So yep. So it's just the gray area.
Got it. Okay.
So we're just going to talk about the gray area now. And what I want to point out here is that the only thing that needs to be touched here or edited are the red items. So in this particular case, if we look at the red items in the middle, the board thickness is 0.06 inches thick. And that's a fairly standard board thickness, and that's what his is. And then I just picked an arbitrary 10 mils for the outer diameter of the via.
Okay.
And this will, once I go through this, I'd like you and I to talk about what's a practical number of vias that you can put in, and we'll go down that road together a little bit after we go through this. Okay.
Absolutely, Mike.
And I also want to touch on plating. So now I arbitrarily picked 0.01 inches for the OD. Now the plating thickness, standard plating thickness in my realm is 1 mil, and probably more like 0.7 of a mil. Would you agree?
I would absolutely agree.
So would you change that 3 mils to, let's just make it 1 mil for argument's sake.
Got it.
Cool. And so that defines the inner diameter there. And also the number of vias. Let's knock that number of vias. What did we see over there? There was about
30. There were 30.
Let's change that to 30.
Okay.
And in reality, we were looking at just one of, so let's start with 6, because there were 6 under each one of the packages.
Got it.
All right. So now if you go over and look at that junction temperature and case temperature, you can see that just for a single FET with 15 watts, you're a little bit, my highest junction temperature that I like to work with is about 125 C. And I didn't look up what the max junction on this FET is, but they typically are going to be around 125.
Okay.
Gallium arsenide, they'll go up to maybe 150 or so, but I haven't touched those guys in a long time. I think 125 is reasonable. And you can see that that junction temperature calculation of 166 is a bit of an issue.
That is pretty high.
And when Sven ran his design, he didn't tell me how many watts he could run, but he couldn't run full 15 watts. So, and he had a case temperature that he measured, I think, with an infrared imager that showed that he had a case temperature of 125. So let's change our power over there, that 15 watts.
Mm-hmm.
Let's change it down to, I don't know, 10. See what that does. Now, the thing is, I'm calculating the case temperature below the chip. And there's a different, and so with this component, you're familiar with cavity up and cavity down, right?
Yes, but our viewers probably aren't.
So let's talk about that a little bit. So in this particular case, the cavity is up, which means that the chip is mounted to some kind of substrate by some kind of epoxy, and then that substrate might be mounted to a header, and it might be mounted just to the case. But either way, if you're looking at from the chip junction going down through the package, it's going right down toward the board. Whereas some packages, it'll be flip-flopped, where that whole configuration would go up to the top of the case. And with this package, they have a different thermal resistance value for the junction to case if if you wanted to have the top of the case. And that thermal resistance is much higher, and I think it was about 20, but I'd have to look it up. We might have it on that other page. Let's back up a little bit and just see if it's there so we can use that. I apologize for not looking that up before.
No, Mike, it's fine. And I know you expected to be driving today.
Scroll down just a little bit. It's right below there. So yeah, so 20, okay, the thermal resistance junction to case top. See that in the middle there on the left-hand side?
Mm-hmm.
So 20 degrees C per watt is the thermal resistance from the junction to the top of the case where he was measuring. So let's go back to that page, put in 20 and see what put in 20 for that junction to case number. Yep. And yeah. So what we have to do now is bump up. I don't think that he really saw 310 degrees C. So there's a little breakdown in the stack up, but let's try to bring that junction temperature down to about 130. Let's put in about 5 watts.
Thermal runaway, anyone?
Yeah, I know, right? And so I don't have a good value for the case temperature that I'd have to go through and look at how I'm calculating that. But I don't think we could get the case temperature up in this configuration to 125 C and not have the package blow up. So, there's limited use of these kind of tools, and you have to dig through to find the best way of assessing how these numbers are stacking up. So the just 5 times 20 is 100 degrees C rise. So the case temperature, let's click on the case temperature down below again, and let's look at that calculation. So I think it's not including the junction to case. Yeah. So what we'd have to do there is pull the that blue window up to capture the 20.
Okay.
If you grab it from the corner, that little one of the corner dots. No, you can go right down to the blue. Yep. Yep. There we go. That should do it. So go ahead and hit return. And now we're just going to get the same thing for the junction temperature. But this case temperature is what we want to target for that 125 C. So let's lower the 5 watts to 3 and see what we get. All right. So it's going to be a little bit more than 3 watts that he probably ran through it. And he was measuring 125 C. Okay. Now, back over to the calculator. So we've got the vias defined. We've got 1 mil of plating in the via. And so the calculation for a single via, if you move your cursor to the left just a little bit, and over in the gray area, you've got the single via R. That's the thermal resistance for a single via with the 1 mil of plating in it. And then down below, I do a calculation to calculate what the thermal resistance, because all of these thermal vias are in parallel with each other. And so they all add up. So with 6 vias, that 217 watts with 6 vias, it drops the thermal resistance through the board to 36 degrees C per watt. Okay.
Mm-hmm.
And so that's the basic calculation just for the thermal vias. Now, so I don't like to just neglect the board, the thermal resistance in the board. And I'm only using the thermal resistance of the dielectric material. If you've got a bunch of copper planes in the board and other vias, there's going to be some kind of composite of the board material and the copper. But for doing these kind of calculations, I like to be on the conservative side, and I don't worry about those things. I just use the thermal conductivity of the board. And so if you look down and then to the right, there's one more red area. That 2 inches is, that 2 square inches is the area of the board that I'm assuming that we've got the thermal vias populated over. And the other part that I wanted to emphasize, in a design like this, you want to have as much copper right underneath the packages as you can and spread the heat out as fast and as far away from the component as possible, and tie your thermal vias into that copper right around the package as much as feasible. So if you go up and change that 6 vias, well, let's change the plating thickness first and look at how that changes. Now, so I set that up as 3 mils, and that would, my concern with 3 mils would be that I might start closing out the via and trapping chemistry inside the via. Would that be a concern of yours on the manufacturing side?
Not so much now with pulse plating. It certainly can be a concern, but I've also seen via samples where, we plate those things solid shut, and you do the cross sections and they look clear. There's not a whole lot of voiding in there anymore like it used to be in earlier years. So I would pretty much always, and of course, I would want to get our process engineers confirming this so they don't beat me with a stick next time they see me. I would say you'd almost always want to increase your plating and get rid of the epoxy fill from a cost standpoint, because we can do it so darn good now. Of course, aspect ratio comes into play. We've got some pretty high aspect ratios going on right now, but I think we could do 1:10 pretty reliably.
Cool. So let's kick that up to 3 mils.
Okay. Oh, not like that. Haha. I broke your spreadsheet. There we go.
Cool. Yeah, and so you drop that thermal resistance through the vias, through 6 vias, from 37 degrees C per watt down to 15.5 degrees C per watt. And that's a significant reduction. And now if we bump the number of vias up to, let's do 30 first, since that's what that design has.
Okay. And I've also got good news for viewers at home. I'm going to share this on screen real quick. We now have this spreadsheet available for you at this address, I'm told. So cool. If you guys want to play along at home, play along at home. Okay, I bumped that up to 30, Mike.
All right, and let's go over to the calculations part. Let's put the junction to case back at 0.9. And also scroll down a little bit, and let's change that calculation so it's not picking up for the case temperature. Let's set the case temperature back to the way it was. So if you just go down and set, yeah.
Got it.
Sweet. All right, now we're not cheating anymore.
Now I'm learning.
Cool. Good for all of us. All right, so I can't see the spreadsheet. I see the Royal Circuits emblem and stuff, but I can't see the
let me get rid of that. That should have been up long enough for it to show up in the chats now. And then I can scroll up for you. How is that, sir?
That looks good. Now, essentially, we should be simulating his design, but you got to wonder about that 125C top case temperature and how this configuration of a model, where the errors are. And what I like about something like this, so this would be in a design where I'm working with a group of people and I'm part of the team. This would be one of the first things I do to kind of get a feel for things. And then I'd go off and start building a more detailed thermal model with the nice thermal modeling tool. And without that, people they're really stuck. And I'll send a message out for Sven here. If he's in electrical engineering group or a department at the university, I highly recommend them teaming with the mechanical engineering department and getting one of their thermal people involved, because both people will gain a lot from it, and they'll be able to have a higher success rate for the next spin that he makes on this design. So let's go up and push that 3 watts up to 15 watts.
Sorry. Here?
Yep. Because it's so hard to have all the disciplines under your belt, right?
Yeah.
I feel for, there was a time period when I first started working that the groups that I was working in, they wanted to have the thermal analysts also be stress analysts. And those are very, very, it takes a lot of time to be good at either one of those disciplines. And to be good at both disciplines is a special individual. And I know a few, but I wasn't one of them. I did my best at doing stress analysis, and I was able to come up to speed okay. But to try and meet the design goals in terms of schedule to do both disciplines, you have to take shortcuts is really what it comes down to. And that's a tough world when you have to start taking a lot of shortcuts.
I remember thermodynamics in college. Not that many people passed. I was quite happy with my B. A lot of super seniors taking that over and over again. It's complicated, and there's a lot to keep track of. And if you forget one thing, you could be done, depending on what that one thing is, of course.
Yeah. So now let's scroll down a little bit more. So on the, let's look at the 60 watts. So on the left there, I've got 60 watts, and I'm just looking at the temperature rise through the board. So we're just using that thermal resistance through the board to see what kind of a temperature rise we have through the board. And I'm also including, a junction temperature there. And let's see. I'm a little confused about that one.
All right. That's okay. It's thermodynamics.
Click on the sum total, 1.7
okay.
there.
The sum total here?
Yeah. Let's see what that's looking at here. Okay. So it's just the 1.73, and that's just the board. So the case temperature, junction temperature don't mean anything there. It's just the temperature rise through the board is what we're looking at. So if you go down to case temperature and you look at what that's looking at, let's see, click up on top. Yeah, so it's just using, temperature above ambient, and it's just the temperature rise across the board with 60 watts. So the goal here is just to see what the temperature rise across just the board is with a full power of 60 watts, and try to see what some more vias would do to try and bring that delta T down. 130 degrees C across the board is not going to be an acceptable temperature rise. And fortunately with these MOSFETs, they've got a very small junction to case thermal resistance. And so we really have to get what that MOSFET's mounted to. We need to get that temperature down. And at this point, there'd also be a lot of work looking at what kind of a heat sink is on the back of the board and how that's going to be mounted. But for the point of talking about thermal vias, let's bump that 30 thermal vias up to 100.
Wow. Okay. Yeah, a lot of your glass transition temperatures for, if you go get a run-of-the-mill cheap FR4, you're looking at about 140 C. So if we've got 120 above 25, you're there. You're melting, you're decomposing your glass fibers. I mean, board's all floppy.
Yeah, not a configuration you want to design to.
No, floppy boards are out this year. Who knew?
Yeah. Yeah, so you're starting to get that delta T down, but at some point there's only so much you can do for the kind of power that is trying to be designed to here. 60 watts is just a significant amount of power to design for, and they're by using a spreadsheet like this, I guess it just helps you start thinking about where your bottlenecks are and what you can do about it. So now, talking about thermal vias, I'd like to get back to what I was asking you. What's a practical, on both from your manufacturing background and your electrical background, Mark, what's practical for getting a population of, say, 100 thermal vias at 10 mil diameter in a particular area?
Well, it's in 2 square inches, it's doable. You start running into upcharges though. Anytime that you have to do a drill hit, that drill can sometimes wander and twist. So you can't always stack them, one next to the other. You've got to put a little bit of separation distance in. I forget the exact number, but our small, okay, so let me back up a little bit. Typically, you don't want to have an aspect ratio greater than 10 to 1. So if we've got a 63 mil board, as you mentioned here, our smallest drill hole would be 6.3 mil. They don't really come in that diameter. Typically, the drills come in increments of 0.05 millimeters. But if you order let's just stick with the English units for a minute, a 6.3 mil via hole, what we do then is we over drill it and then we plate it down to that size, right? So we're not going to drill a 6.3 and then plate it down to a 4.2. We're going to drill, a 7 mil and then plate it down to a 6.3. Or whatever the metric equivalents would be. I don't know them off the top of my thing. So you've got to keep those drills spaced at whatever your manufacturer minimums are. I'm sure we could get, a 10 by 10 and 2 inches without much difficulty. But my next question would be on the assembly side. How much of the solder paste is going to start wicking down into those holes, right? If you leave open via holes and you put solder paste on that, it just capillary action plus gravity is just going to suck that solder in away from your part, and you're going to end up with an air gap between your pad and your land pad and your part pad. And air is an incredible insulator, right? Great insulator. So then we're going to have to talk in a second about how you would coat those, how you would cover them. But I'm going back to something I remember from, I want to say J Standard 01, or it might be in 600A, I don't remember. But you can have as much as 50% voiding from land pad to part pad and still consider that part acceptable. What would that do to our thermal resistance, Mike?
So explain that part one more time.
Okay, so if you have a bunch of holes that the solder paste can wick into, you can get air voids between the part pad and the land pad. And as long as there's less than 50% voiding, so as long as there's a 50% connection between the land pad and the part pad, then we would call that acceptable from an assembly standpoint. But what would that do to our numbers on this worksheet? Wouldn't that?
Well, the via for the thermal via, or
not for the thermal via, but for the I guess that would be your case to board number, would double it at least, wouldn't it?
Well, the case to board number is based on the area of the package size itself. And he's got a thermal pad between the package and the board. So that would fill over all of any kind of interface, any kind of surface roughness or anything on the board side and between the board and the component. Just fills in all the gaps.
I will bring up a graphic just to show you the people what we're talking about. So anyways, back to your question, can we drill the holes? Yeah, we can drill the holes. But if you start doing this a lot, and you're doing this over your whole panel, you could start looking at upcharges from your fabricator. More drills, more wear, and they've got to replace them more often, more chance of breaking the drill off in the board, having to chuck the panel if they can't get it back out. There's a lot of considerations.
The other concern that I think about is the Swiss cheese effect that will occur in your big copper conductors coming in to feed those FETs. So that has to be managed as well. But
yeah, you could start getting barrel wall failures and all sorts of stuff.
Yeah. But you got to get it thermally to where it needs to be to work. So it's always a happy medium between all the different disciplines.
So it seems then, what if we did a slightly larger diameter hole with more plating? Would that be something you recommend?
Well, that's the fun part. That's why the tool's here for people to go in and make those kind of changes and see how that affects the end result. And then do more homework on some of those areas that, I don't know what the design has for numbers, like the sink to air and the conduction through the sink. put real numbers in, and then just experiment with the number of vias and look at how the calculations are made so that you can make this a tool for yourself.
All right, I'm going to share a new screen with you. Going back to something I brought up, but I didn't really set down. I don't have slides. Do I have to stop screen first and then share? Window. Well, this is the window, but that's not the thing I want to show. There we go. All right, so here we're looking at a thermal pad on I don't want to count that, but it's a QFN package with a thermal pad in the middle. And if you look, all of the vias that are underneath here became sources for voiding, right?
Interesting.
That's incredibly common. The solder paste in that area will wick down into the holes, gases will come up, and you'll end up with voids around virtually every single one of them. And like I said, if you have as much as 50% voiding, right up until you get at 49% voiding, that thing's still acceptable to go out the doors by IPC standards. So what do you do with those vias? You can leave them open and really upset your assembly house. You can tint them, close them off. You can plate them so that the hole's so small that the amount of solder paste that comes down is insignificant. Or you can look at some advanced assembly techniques, like vapor phase reflow, vacuum vapor phase reflow, where we'll assemble your board in a light vacuum. So all those gases, and then that just becomes a monolithic piece. But then there's also, if you do have thermal vias under a package, I want to say it's IPC 70, God, I always forget these numbers, 7035 or 7096, I never remember. But there's a new standard out that tells you how to place your thermal vias in a particular pattern with solder mask dams around the vias, so that you don't have the problem of the solder paste, wicking into that hole.
Yeah.
So,
that's good.
Interesting. Yeah.
And of course, all of those are cost adders, any extra steps that you have to include in your manufacturing process, right?
It is. So if you leave it open, you're going to have to rework more often than not. So that's why this, I want to say it's 7093 is the land patterns that we recommend, because that's the cheapest way. It's because you've already got solder mask on your board. So just putting it in a particular pattern, that's free.
Cool.
As far as the price goes. And filling with epoxy fill is ridiculously expensive. So that's why we usually recommend increasing your plating first before you start looking at a thermal epoxy fill.
Nice.
So, yeah.
So
and then
I'd like
we've got questions too. I don't know how long you have, but did you want to hear a question or two?
Sure.
Okay. And then I will bring up our slides while we're doing it. So the first question we have is from Mr. Daniel Beaker. What impact can you expect with conductive thermal fill?
I almost added that to the calculator, because the issue is that the thermal via fills typically do not have a very high thermal conductivity. And the addition, if you think about the volume of the thermal via fill and what the thermal resistance through that little piece of fill looks like, especially if you've already plated up your vias. And I've never seen a case yet to where the thermal via fill actually helps thermally. If you have to fill them, that's fine. I'd go with the cheapest ones possible, but make sure you plate up. Just plating up is going to give the most value from a thermal perspective, and it'll do a lot more for the design. And I would love to get into an argument with the people with thermal via fills and go through that.
Oh, you want an argument? Daniel Beaker is here to play. He says 100 vias in that space is not practical in any design. Now, that's in direct contrary, assumingly, to what I said, where you asked if we could do it. I said we could do it. Yeah, it's a horrible idea. You can
Right.
drive with your feet too. So Daniel Beaker, you're looking for an argument. I'm not going to give you one. You're right.
Yeah, well, and that's the point of these first steps, is to look at what's practical. If you need 100 thermal vias and it's not a doable thing, well, maybe we start looking at some other solutions. You know, how much copper can you add to that stack up to help spread that heat out, so you don't have this huge concentration of power, and maybe spread those MOSFETs out if you can. And it brings up all these kind of questions that just get you down the road. All we want to do is look at the calculation of the thermal via here. And now the practical side, that's why we're bringing it up with Mark and throwing it out there. You know, there's first steps in the design, you know, and one first step in this particular case is, can we do 60 watts of power on all these MOSFETs? And the first look is, well, not very easy. And it's not a simple problem. It needs to be worked, and one step at a time.
Yeah. We've got a few more, and then if you have time, we'll get back to the presentation. Does solder mask webbing to control pastry distribution during reflow make sense? What is the thermal conductivity of mask versus air void? Okay, great questions. So does it make sense? Yes, it does. And that's, hopefully somebody in the comments that knows the IPC standards off the top of their head can tell me which one, because I hate to keep saying the same number if it's wrong. But yes, that's what you're doing. With the liquid solder masks, you know, we can do webbing down to 2-3 mils. As long as you have a solder dam, it repels the liquid solder paste, and it can keep it in the areas that you want it to. So you want those solder dams around, you know, vias in pads, vias near pads. You don't want that. But the question is, what's the thermal conductivity of mask versus air? Do you happen to know those numbers off the top of your head? I don't.
No, but I've got a general feel for them. You know, thermal conductivity air is about an order of magnitude worse than the dielectric materials. And, you know, solder mask is probably similar to the board dielectric materials, not orders of magnitude different or anything. So, you know, they're all poor conductors, and air is, you know, a real poor conductor. Order of magnitude probably different than the thermal conductivity of the board dielectric materials.
And thermal conductivity of board dielectric materials are in the order of what, about 0.4 watts per meter Kelvin?
Yeah, 0.3. You know, I've got some numbers on the spreadsheet there that I have. The numbers that I included are measured values that came from some of the work that we did with IPC 2152. We had polyimide boards, and we had 2 different FR4 boards. We had the thermal conductivity measured for each of them. And what you typically get for thermal properties with dielectric materials is the Z-axis thermal conductivity. They don't go and measure the X and Y, because you've got, you know, different materials that are making up the different boards. And so you've got different size materials that are in the weave. And so in the calculator, if you go to the right, I think I included it on this page. Can you go way over to the right, Mark? Yeah, there you go.
Sorry, it's just taking a second.
That table 1A, 1B are FR4 boards, and the polyimide is the polyimide board. And one of the differences there is that the thickness of the boards is a little different. I guess in these, they basically use the same. It's a little different. But the coupons that were made, those properties were all measured, and that's what we were able to use when we started making our thermal models for correlating with the data that went into IPC 2152. The other thing I wanted to, you know, touch on is that power calculator page. And I know you didn't want to spend too much time on the differences in the electrical resistivity of copper, but I do like touching on it because that haunted me for 2 years. So if we look, this calculator is, again, the red values are for input. So the input values are kind of over on the right in the L column. And all that this does is it calculates the power dissipation in an electrical trace. And it assumes that this is a perfect geometry. And so some of the values that go into that, one is the resistivity of copper. And the three values that are included up on the upper left there, the resistivity values, the first one comes from the CRC Handbook of Chemistry and Physics, which I thought would have been a great value for using to calculate the thermal resistance in a copper trace. But it turns out that that's a very pure copper. And the next two values, and it's a little strange at first, but the first value there is for 1/2 ounce copper, and then the next one down is for 1 ounce copper and greater. And those values come out of a particular test method, which is an IPC test method 650, 2.5, 0.4, 0.1, and that's actually 0.1A. And those values were determined by measurement by the National Bureau of Standards back in the 50s when they did their original testing. And those values gave me just the most perfect correlation when I was looking at trace resistance. And when I was looking at trace resistance, I was also looking at the trace cross-sectional area. And these values gave me just a perfect, almost perfect correlation between the trace cross-sectional area, which we had cut up and measured, so calculating and then measured, those values gave us a very high correlation between the test traces that we were working with when we were doing all the test data collection for IPC 2152. And I highly recommend those two values in there. And the point here of this calculator is just to calculate the power at a given temperature. So if you look at applying current to a trace, and if you look at measuring its resistance with just low current, something where you're not really heating the trace, it'll have a certain resistance. Well, when you start kicking up the amperage and the trace starts to heat up, then the resistance changes and you have higher power at the steady state temperature that you're at in its actual use. So if you have a board that it's operating at say 85 degrees C, which would be kind of an average board temperature for a lot of the designs that I used to work on, it's important to assess what the power at temperature is at when it's under use, and not just estimating power at a ambient temperature for the trace. So this calculator you have to play around with a little bit, but it includes the trace length. So right now it's set at 1/2 an inch wide. If you look up at column L, 1/2 inch wide, it's 5 inches long. 2 ounce copper, I've got it set assuming that 1 ounce copper is 1.35 mils, but my experience is that copper, 1 ounce copper is more like about 1.2 mils, maybe a little bit more. And if you look at the IPC minimums, trace thicknesses can be significantly lower. And so it's worth playing around with the copper thickness a little bit. And then this just calculates a delta T for the using, let's see, there's an ambient. If you click on that one, click on that 108 degrees C, and then go. So that's just hardwired in.
Yeah.
So it's just being used to calculate the change in power. That's where I would set that at maybe 85 C, and see what the power for the trace would be, if you're running high current. So this is not calculating temperatures, it's just calculating the power in the trace at temperature. And it looks like we're about 2 minutes out from close, so I just wanted to bring those things up and let people play around with it.
All right. Do you have time for a couple more comments or questions?
Sure.
Okay, so going back to before we came up, we were talking with Dan, and he said, so there's no real good return on investment for thermal field, better to plate up. I would agree. I think I heard you say you would agree too, right?
Absolutely.
Yeah.
Unless you have to have it filled with something, I would certainly plate up first and then follow up with whatever my manufacturer would recommend.
So Les is commenting on the IPC specs, basically says have a fill specified amount in the, okay, so you've got data sheets, and this is something you'd want to communicate over to your assembler. If you do have a hot part like that, specify that you require the higher fill amount. They might require you to move from, say, convective reflow to like a vapor phase. I mean, you can get like 90, 100% fill on that. It looks like there's a conversation. What's this? It looks like there's a conversation happening in comments. You really need to do several in parallel so you can have more surface area and lower power per device by more of, I don't know if I understand that one, Dan. I think that there's a separate conversation I'm missing. We got thank you, Les, and Daniel, thank you. Okay, so just to revisit everything, Mike, thank you so much very much for your time. We have already posted your calculator at this web address. For those of you, you should have that in your comments, whether you're at LinkedIn or YouTube. This was our first time trying out a LinkedIn webinar. I don't know how it went on your end, but if you have any comments, let me know. And if it went well, we can actually move it over to the brand channels for the next one. Mike, you said you wanted to do this all again with your software.
Well, I would like to go and talk about IPC 2152.
Okay.
And technology-specific design charts. And I can best do that through using some software that I developed back in the 2000, 2004 timeframe. It doesn't exist anymore except on my computer, but it would at least allow people to see, a little bit more information about trace heating, what it really looks like, and from the perspective of board size, the influence of copper planes, and just be able to talk about that a little bit more than what you can find in IPC 2152.
I'd love to.
A nice way to close out this whole little path that we've been on for a little bit here.
I've really enjoyed this path, Mike. I geek out on this stuff. It's been fun. So thank you so much for your time, everyone. Thank you to Mike Jouppi, Mike Jouppi, for helping us out. And once we figure out a time that works for Mike, we'll set that up. We'll do this all again. So thank you, everyone. Have a great day. Bye.
Bye, Mark.